Baryonic asymmetry is the phenomenon of the observable universe having more matter than antimatter. This is a puzzling problem in physics and cosmology, as the standard theories of particle physics and general relativity do not explain why this should be the case. Basic assumptions of modern physics is that the laws of nature are symmetric, meaning that they do not change if we swap matter and antimatter, or left and right, or past and future. However, some experiments have shown that these symmetries are not perfect, and that there are slight differences in how matter and antimatter behave. For example, in 1964, it was discovered that some particles called kaons decay differently depending on whether they are matter or antimatter. This phenomenon is called CP violation, and it implies that the universe is not symmetric under the combined operation of charge conjugation, C, and parity inversion, P. CP violation is one of the necessary conditions for baryonic asymmetry, as proposed by Andrei Sakharov in 1967. Sakharov also suggested two other conditions: baryon number violation and departure from thermal equilibrium. Baryon number is a quantum number that counts the number of baryons, matter particles made of three quarks, such as protons and neutrons, minus the number of antibaryons. Baryon number violation means that some processes can create or destroy baryons, changing the total baryon number of the universe. Thermal equilibrium means that the system is in a state of maximum entropy, where all the possible states are equally probable. Departure from thermal equilibrium means that some states are more likely than others, creating a bias towards matter or antimatter. If these three conditions are satisfied, then it is possible that the universe started with equal amounts of matter and antimatter, but due to some asymmetrical interactions, a small excess of matter was generated over antimatter. This excess was then amplified by the expansion of the universe, and survived the annihilation of most of the matter and antimatter. The remaining matter is what we observe today as the baryonic matter of the universe. There are several theoretical models that try to explain how baryonic asymmetry could have occurred in the early universe. One of them is electroweak baryogenesis, which assumes that the baryon number was violated during the electroweak phase transition when the electromagnetic and weak forces separated. Another one is GUT baryogenesis, which assumes that the baryon number was violated during or shortly after the grand unification epoch when all the forces were unified. These models typically involve new particles and interactions that are beyond the standard model of particle physics and have not been observed experimentally yet. Baryonic asymmetry is one of the unsolved problems in physics, and it has profound implications for our understanding of the origin and evolution of the universe. It also raises philosophical questions about the nature and meaning of existence and why we are here. By studying baryonic asymmetry, we hope to gain more insight into the fundamental laws of nature and the mysteries of the cosmos.